Hello again. Let me start sharing. All right, so now I'm going to show you an example about how we should be careful about transforming vectors. And there will be more complications, especially when we perform non-uniform scaling. We are going to talk about that as well. And I'm going to give you some links to some nice tutorials about these. All right, but let's consider um, a plane. A line segment like this. Okay, it may be a plane in 3 dimensions. All right, so its normal may be this. So its normal vector maybe just 0, 1. As you can see, this normal is straight up. It's a vertical line that goes towards up. And these are the points, point 1 and point 2. These are the two endpoints of our line segment. Imagine I want to move this point 1 and point 2 up by translating them, for example, 10 units. I want to move this P1 and P2 up by 10 units. P1, P2. Okay, P1x is going to be P1x plus 10. So its x coordinate doesn't change, as you can see, but its y coordinate is going to be is going to be increased by 10. So in other words, I apply this transformation: 0, not 0, 1, 0, 0, 0, 1, 10, 0, 0, 1. So if you apply it on P1, P1x, P1y, and 1, as you can see, its y coordinate is going to be increased by 10. P2's y coordinate is also going to be increased by 10. Now, if you apply the same thing to our normal vector 0, 1, 0, 0, 1, which is, if you represent again in homogeneous coordinates, the third one, what will happen is that it's new. I mean, if you just add 10 to its y coordinate, it will become, so if you do this 0, 0, 1, you will see that it's going to be the vector 0, 11. Actually, it doesn't change anything here. I should have made the example wrong. If you move in the normal direction, nothing changes. But imagine now, okay, it's now 0, 11. It's still the same vector. It's just scaled. You can normalize it, and it will be turned. If you turn it back to normal size, it will become 0, 1 again. Okay, nothing. This is not a problem if we moved in the normal direction. But what if now I move the same vector in x direction? Okay, now my transformation matrix is, so whatever I have here, its x coordinate is going to be increased. Okay, so imagine this same thing is moved towards right. Its normal should still be 0, 1, right? But what will happen is that if you add x, if you add some value to its x coordinate, our normal vector is going to, after this movement, it's going to be something like this. If you add some x value to this, it will no longer, it will be a vector like, for example, 5, 1 vector. Okay, if you add 5 to the x coordinate of both of those values, if you move P1 and P2 towards right, adding 5 to their x coordinates, you don't want to add the x coordinate 5 to the normal vector, because the normal vector again did not change. Translation should not affect the normal vectors. So if you move something, okay, if you rotate, the normal vector is going to change, but it should not be affected by translation. The normal is always facing up, so translation should not affect it. How can we have translation not affecting our normal vectors? One way to do that is, for normal vectors specifically, we use, instead of using 1 as the homogeneous coordinate, let's use 0 for that. But mathematically that will be not so correct, because it's in two-dimensional version. It will be 0 divided by 0 and 1 divided by 0 if you treat this normal. But we will treat normals as an exception. this third dimension, we will use it so that we are going to undo the effects of translation. If we have 0 in this last dimension, anything we have in the last row is going to be multiplied by 0. So the translation is not going to affect. Translation effects on the points will not be affected on the vectors. So this is one thing how we can achieve this thing. Now for rotations, it will not be a problem. We will be able to rotate the vectors normally, but we are going to see non-uniform scaling also helps vector bend in an unwanted way. And for that, I'm going to show you two links. First, one of them is from Scratch Pixel 2.0. It's a nice tutorial website. It talks about what's a normal, things like that, and how do we transform normals. And it talks about, and I'm going to paste this link on the chat box so you can also read it on your spare time. But look at this. We have a line segment AB, and the normal vector is shown like this correctly as 1, 1. Now, if you perform a non-uniform scaling, imagine we do not scale the y-axis, but we scale the x-axis by 2 units. Okay, the x-coordinate by 2 units. The point A is not going to change because it was 0, 1. If you multiply only the x-coordinate by 2, it will still be 0, 1. But however, the point B, as you can see, it became 0, 2. Now this is the non-uniformly scaled line. And if you do the same thing on the normal vector, 1, 1, okay, if you just non-uniform scale, just multiply the x-coordinate by 2, it will be the vector 2, 1. If you draw the vector 2, 1 on this plane or on this line segment, as you can see, it no longer represents the normal vector of this line correctly. So non-uniform scaling destroyed our normal vectors as well. So the thing that in order to solve this problem, we need to do something else. We need to think about what the normal should look like. A vector which should get, if you take the dot product of your normal vector with these points, with this line segment, with this direction, it should still get us 0. What kind of a vector can give us 0? If we do that, it turns out that our normal vector actually should be the inverse of whatever I'm going to go to the slides actually for this to go step by step. All right. So this is actually described, here in these parts of the slides. After we talked about rotation, but I'm going to come to that later again. So here, transforming normals, yeah, right here. Now I'm going to talk about this transforming normals. And the example is also shown by a non-uniform scale. It's a similar example, as you can see, to the line. This time we have a non-uniform scale in which we increment the x-axis. We triple the x-axis coordinates while the y-axis doesn't change. So the line becomes like this. And if we do the same thing for the normal vector, so this is the normalized version of the normal vector. It's the 1, 1 vector, the same 1, 1 vector that I showed before, but it's normalized. 1, 1 is not a normal unit size vector. Its unit sizes, you have to divide it by its length. It has to be 1 divided by square root of 2, 1 divided by square root of 2. So this was the original normal vector. If you apply scaling on it like this, it no longer represents the normal of this plane correctly. So what do? It's not a unit vector anymore. That's another thing. You can normalize it. Making a unit vector is not so difficult. You can just divide everything by divide every dimension by the total length of the vector, and you can rescale it so that it becomes a unit vector. But the problem is not just not being a unit vector. Its direction is wrong. So how can we solve this? So here, the thing about the normal vectors, when we have this as 0, we have solved it by making this last dimension as 0. We solved the translation problem. Okay, so rotation and translation of these normal vectors with the last dimension 0 will have no problems. because all transformations are combined into a single matrix, we should consider the general case in which we may have scaling transformations which are non-uniform. Those are the transformations that will make the normal vector bad. Now, the normal vector's main property is that actually it also comes from the plane equation, that given any 2 points on the plane, the normal vector, the dot product of the normal vector with b minus a, which is this v vector, should be 0. That's what a perpendicular vector, an orthogonal vector, should have, this property, the dot product being 0. Now, if I transform my points, okay, whatever this v prime is, the correct normal vector should still be the correct normal vector, and it should still give 0. So this v prime is the vector in which the modeling transformation is applied on it. Okay, so if I scale this, for example, if you scale b, by the way, that's another thing. If the vector v shows is the vector between from some point A to point B, if you apply transformations on this, the new modified vector v will exactly be the same thing. I mean, if you apply the same modeling transformation to A and B, since these are linear, and since you're also just subtracting this vector v, is just b minus a. So what I'm trying to say is, let me write it here with pointer options, pen. All right. So b. Oops, why isn't it writing? Sometimes this happens. I need to stop this. Actually, they are there. Okay, keep. Okay, I was drawing and it wasn't showing. It's really interesting. So that's like a bug. So what I was trying to say is that if you have 2 points like this, and this is your vector b, right? So and you're going to apply transformation on these. So it's going to be like mb minus ma. So mb minus ma like this in these matrix form will be the same thing as mb minus a. So you can apply your whatever your modeling transformation to the vector directly. So your v prime, the transform v prime, whether it's uniform scaling, rotational, or translation, will be just if you apply this transformation to your endpoints individually, it will be affected similarly. Now the problem here was the normal vector. The normal vector should be in such a way that what should be the matrix Z? We should multiply the original normal vector. The problem we were talking about is that this Z is not equal to M. If we have already seen that, because in this example, in the previous slide here, if you multiply n with the same m, it doesn't give you the m prime. The correct m prime is this. Okay, so this is m prime. But if you multiply your n, this original n, if you multiply it with your modeling matrix, it doesn't give you m prime. That's a difficult thing to do. So what should be the correct matrix that we should use instead of m? This is what these slides are about. How do we find that z? So what we know is that the dot product of v prime and zn, so whatever, this is the correct one. So if I take the dot product of this zn with v prime, I should get 0. This is what I know. And I know the normal vector, I know this one, so how can you get 0? So it's written here. So they should be, the m prime and v prime, their dot product should be 0. And which means that, they're also here in order to perform this computation nicely, what this z should be. So it turns out that you can find z with respect to the original modeling viewing matrix. Okay, so and the derivation is here. If their dot product is 0, we can actually take the dot product is written in matrix multiplication. So what is the dot product? The dot product is, for example, if I have x, y, z here, if I take the dot product, I'm multiplying these individual things, right? Now in this, this was the dot product. This is matrix form. In matrix form, if I have a normal vector, nx, ny, and z, okay, sorry, nx, ny, and z, this is my normal vector. Actually, these are m prime. Okay, I want to take the dot product of, and it's like 0 like this, and I want to take the dot product of this with v prime x, v prime y, and v prime z. Okay, it's 1. This is not a normal vector. This is a regular vector, which is the line segment between these 2 points. Now, this is a 4 by 1 matrix, right? The normal vector. This is also 4 by 1. Can you write the dot product in terms of matrix multiplications? Can you multiply a 4 by 1 matrix with a 4 by 1 matrix? No, you cannot, because they're not you cannot take the product. So what we need to do is, if you take the transpose of this, meaning that if you make this column matrix a row matrix, if you take it like this, nx, ny, and z 0, it's possible to multiply a 1 by 4 matrix with a 4 by 1 matrix, and that's what dot product is actually. A dot product in matrix form is if you take the transpose of this, and the result will be a 1 by 1 matrix, which is that scalar, which is that 0 that we're looking for. That's the purpose of this transpose, to write the dot product in terms of matrix multiplication. Now, here I know that I already told you that this is what v prime is. Okay, v prime is just this model transform. If you perform the modeling transformation on v, we get the v prime. Now, here, in order to be able to do this, we also know that this n and m prime t is going to be, you're going to get if we can multiply the original normal vector with the correct z matrix, we are going to get the m prime. This is the definition of m prime. Okay, and we want to figure out how we can get m prime by multiplying z with n. Okay, and this one is the same thing written in transpose form. So a 4 by 4 multiplied by, sorry, this was 4 by 4 multiplied by 4 by 1. You can get its transpose by, if you want to change their size, if you take the transpose of this, it becomes 1 by 4. Okay, and if you multiply it, if you, instead of right multiplying it, you may also left multiply it, and this is how you can do that. If you take the transpose of both, it will give you the same m prime vector. So this is that m prime. Okay, it's actually the transpose of the m prime. And here we get this equation. The only unknown in this equation is this matrix. We have the modeling transformation matrix, we have the original normal vector, we have the v. So we need to get this to be 0. If these two matrices multiplied, if this is the identity matrix, the relationship will be preserved. I mean, because we want the normal vector, this v should be 0. This relationship will only be preserved if the multiplication of these two are identity matrix, because we want these two to be 0, to be orthogonal to each other. So here, therefore, the only way this equation is going to work out correctly is to have this VTM to be the identity matrix. And from that, Z turns out to be M minus M. We take the inverse of our original modeling matrix and we take the transpose of it, we get ourselves Z. The good thing about this modeling transformation matrix is that its inverse transpose is equal to transpose inverse, and because for a square M by M matrix M, they are equal to each other. I mean, these two entities are equal, and therefore we find our normal transformation matrix. So this Z is sometimes called the normal transformation matrix, which we will need especially when we have a non-uniform scaling. Okay, so this is this side note was about how we transform our normal vectors correctly. From this you should know that it's something related with you need to take the inverse of your transpose matrix, inverse of your regular modeling matrix, and take the transpose it. If you multiply your normal original normal vectors with this matrix, you will get correct normal m primes. So OpenGL has actually a separate matrix that is used for this. All right. And also what actually it does is, instead of having the last component a 0 in the vectors, I think the transformation matrix you can use is just you can use a 3x3 matrix for that. But I just don't want to confuse you. I think it's still a 4x4 matrix. I may be wrong in that regard. I will also share with you another tutorial, and there are a bunch of nice tutorials in this guy's website, Song Ha. I think he is South Korean. It's this one, Song Ho. Sorry, actually it's from Canada. It's hosted in Canada. So this link that I just shared in the chat box, it also talk about OpenGL. How do we perform normal vector transformation in OpenGL? It talks about how we find this. It's the same thing here. Take the inverse of the original modeling matrix and take the transpose of that in order to transform your original normal vectors in the transformed version. And why we need to do that is written nicely here. There are also nice tutorials in general about OpenGL in this guy's website. It talks about the forward rendering pipeline too, and all those transformation matrices. So you can use this as a reference and as an additional resource to learn on these transformations better. Now, if we look at these modeling transformation slides, the thing that I want to discuss is this alternative method we are going to use in rotation around arbitrary axis. But let's go back to going in order in these transformation slides. We talked about homogeneous coordinates. We have talked about the homogeneous coordinates help us have all of these basic transformations. I told you that translation, rotation, and scaling are our basic transformations, and we can sometimes, instead of writing the matrix matrix form, for example, if in the exam we talk about these things, sometimes we just don't want you to do the multiplication of the matrices on your own, but give it as a sequence of basic transformations. In that case, you will be writing your solution as a call to basic transformations like this. So if we ask you the question about this mirror case, for example, the mirror question, the answer to this mirror question was something like this: translate P2 to origin, make the rotation of that alpha degrees so that P2 is aligned, and this alpha is found by some equations that you provide. Perform the reflection. We can call that reflection, for example, 0 minus 1 parameter. Perform the reflection with this -1 scaling and undo the alpha degree rotation and undo the translation. Okay, so sometimes you can give your solution as a sequence of matrix multiplications like this that is indicated by just having calls to these basic transformation matrices. Okay, so actually this is like what I have written here is 4x4 multiplication of 5 4x4 matrices. So the result will be another 4x4 matrix, but sometimes it's sufficient to have the solution just as a call to these basic transformations. Now, we talked about transforming vectors, and we talked about how we compose transformations by right multiplying our point with these transformations. And M1 is the first transformation that is applied. And if you compose, and you can compose different types of transformations. I'm skipping these one. You can, for example, what does it mean to rotate around origin 5 degrees first and theta degrees next? If you do the multiplication, actually you'll find yourself the solution uh, to rotate theta plus 5 degrees. Okay, so here the thing, these are here the cosine of theta plus phi. And if you scale an object repetitively, it's the same as multiplying the parameters. These are composite transformations which we do not use regularly, actually. And we talked about rotation around the pivot point. We first rotate, translate to origin, rotate, and translate back in 3 steps. And here is the solution written like this. If you multiply these matrices, you get the formula in the earlier slides. We talked about scaling with respect to a fixed point. So when you're scaling, if you don't want to move your point, if you want to scale with respect to center of mass, you first move the center of mass to origin, you do the scale, then you move back. And this slide is nice. It was, I think, from Hernan Baker's textbook. It shows why order of compositions, order of these matrix multiplications is important, because matrix multiplication is not commutative. And it shows, for example, the same object. Okay, now the object, I think, is this one. So here, let's see, this is the first thing we do is perform rotation, and this is the pivot point. So you first rotate around pivot point 90 degrees, and you get here. And so yeah, so it's a 90-degree rotation around this pivot point. So this is the original triangle. So the red one, the solid red triangle, is our original triangle. Now the transformations are exactly the same. Translate in the y direction this amount and rotate around the pivot point 90 degrees. If we perform the rotation first and then move later, the triangle will be here. But let's try the same thing in reverse order. Translate first and then rotate 90 degrees. The triangle is going to be here. So we just first translate it, and this dashed triangle is then rotated around this pivot point 90 degrees. After its rotation, it's going to be this one. As you can see, this triangle, the hollow triangle, solid hollow triangle, in both cases are in different places. So order does matter. We talked about reflection, which was a special case of scaling. There is one other transform which I have never used in my life in a real OpenGL application, but it's also a linear transform in which we can use in maybe certain applications, for example, for like a deck of cards. We can maybe use that. It's called shear transform, in which, sorry, the cat needs some attention. Okay, so what it means is that you can add to a coordinate. For example, the x coordinate is translated with respect to what the y coordinate is. You may have, so this is still a linear transform. X prime is equal to 1 times x plus some b times y. Okay, so it's a really interesting transform. If you have something like this, let me write it here. So x prime is equal to x plus some by. So this is called shear transform. Okay, if this b is, for example, it can be any constant. It's called the shear. It's like shear factor. Like fear factor. This is the shear factor that we apply on y. So the larger the y coordinate. So if you have an object like this, okay, the larger the y coordinate, more it will move towards right if it's positive. Okay, the smaller the y coordinate, it will not move to the right. If you have multiple vectors, vertices that are here, okay, the effect will be something like this. If it's at the top, it's going to move more. If it's at the bottom, it's going to move less. So this is called shear transform. As I said, I have never used shear transform here in an OpenGL application before. We have talked about three-dimensional transformations in general. Like translation is really easy to extend to 3 dimensions. rotation around major axes is easy because our 2D rotation actually is rotation around z-axis. So if you think about the original 3 by 3 matrix, if you take its top 2 by 2 part and put it into a 4 by 4 matrix, you will have a rotation around z-axis because our just think about we were rotating on the xy plane around origin. That origin rotation around origin on the xy plane corresponds to rotation around z-axis. So if you look at this last row, last formula here, if you look at this cos theta minus sin theta, cos theta, the first 3 by 3 part of this matrix is exactly the same as 2D rotation around origin. Okay, now the other ones are just rotated versions of the original one because if you think about rotation around x-z-axis is like now think about z as your x coordinate, x as your y coordinate. If x was your y coordinate and z was your x coordinate, it will be the same as rotation around origin. And this is exactly what we do. We change the we place those cos theta minus sin theta in such a way that whatever we had written in the x now is written in the y. So if you rotate around y-axis, if you take a look at that, rotate around y-axis, whatever we had written in y, but is it in reverse order? Yeah, so rotation around y, so minus sin theta cos theta. It seems like it's not. I would expect this should be cos minus sin. Let's see. Look at this. If you look at rotation around y-axis, x is like y, z is like regular x. I would assume rotation around y would simply be the z will be just cos minus sin. I'm not sure why we have this one here, rotation around y. Oh, maybe the orientation is wrong. No, the orientation is also right. This is, if you make this whatever we had in the y previously, if you write it here, it should work, right? Maybe they turn out to be the same thing. I'm not sure, but you can check these. The main reason here, I mean, the main thing that I want to say here is that the rotation around major axes are just like 2D rotations. They only have a single component here, which is like a subset of that. It's like the two-dimensional rotation matrix. Now, the variations of this rotation, the arbitrary rotations that we may want is, what if we want to rotate around an arbitrary axis which is parallel to one of the major axes? This is the easiest case actually. If you try to rotate around some line which is parallel to the x-axis, if it's parallel to the x-axis, this line could be indicated by if you know the point on the yz plane where this line intersects, it's going to have x coordinates 0. And what you will do is, if you move this line onto x-axis and moving the line onto x-axis, aligning this line with the x-axis is just a simple translation. Okay, so if you want to rotate around an arbitrary axis which happens to be parallel to one of the major axes, you just need one translation to align that rotation axis on that major axis. So this is really the easy case. The difficult case is this: rotating around a really arbitrary axis. What is written in 5 steps here is actually 7 steps, because the step 2 requires 2 basic rotations, because there are 2 angles. As I indicated earlier, if you let me remind you what those 2 angles are. Let me get a new whiteboard. So if we have an arbitrary vector, imagine we have an arbitrary vector that passes through the origin. Okay, so this is some arbitrary vector that passes through origin. Now there are 2 angles that are associated here, that are associated with this vector, considering the major planes. One of them is how high this vector is. For example, I can have a vector. It's really difficult to show in 3 dimensions, but imagine I draw a vector here, which is almost on the x-axis, but it's not. If you take the projection of this on the x-axis, on the, sorry, xz plane. So let me have it from the beginning. So this is z. Let me have it a little bit tilted. This is y. This is x. So what I want to say is that if we have a vector that is like this, if I take its projection on the xz plane, if I put it down, it will be this angle. Okay, imagine I have the same thing and I tilt it up. Okay, and this projection still is on this vector. How it happens is that there are two angles. One of them is this theta, which shows how high it is from the xz plane. So the angle this vector makes with the xz plane. The other angle is that the angle this vector makes with the xy plane. So this is the xy plane and this alpha is that angle. So it may be close to the xy plane, just requires a small pushing to the xy plane, but it requires a large amount of pushing down so that it's on the xz plane. So therefore, if you want to align this vector with the x-axis, you need to first push it down. Pushing it down simply means that we rotate it around z-axis. If you rotate it around z-axis, you may push it down like this. And then when you rotate it around x-axis, around y-axis, and then when you rotate it around y-axis, you can align it with the x-axis. So there are two rotations we are going to perform: basic rotation around z-axis, and we are going to perform basic rotation around y-axis, and they will be in different angles. One of them will be theta minus theta, or whatever angle is. The other is going to be alpha. So there are two angles we are going to rotate around major axes, and therefore this step 2 actually is 2 steps, and which makes step 4 also 2 steps. So the total number of steps in this method is 7 steps. So these are explained here like this. So if this is the arbitrary axis that we want to rotate around from P1 to P2, we first move P1 to origin. We could have moved P2 to origin as well, it doesn't matter. So any point, you could have moved P1 plus P2 divided by 2, the midpoint to origin, it doesn't matter, okay? The important thing here is our goal is to align this arbitrary axis to one of the major axes of our choice. We can try to align it with the x-axis, we can try to align it with the z-axis or y-axis. Okay, so in this example, it tries to align it with the z-axis. So we first move it here. So this is step 1. In step 2, which requires 2 rotations, we align it with the z-axis. Then we perform the actual rotation that we want to perform, and then we undo the rotation in step 2, and we undo the translation in step 1. So, and the mathematics of it is like this. We first determine the vector that is the axis of along the axis of rotation by P2 minus P1, okay, and the unit vector along V will simply be this. We normalize it, let's call it ABC. Okay, so here ABC are the values of this vector that shows this vector from P1 to P2, and we make it a unit vector. Okay, we make it a unit vector on P1, P2. So let's call this ABC. We are going to use these ABCs to find those alphas and theta. So by the way, you really don't need to find the actual angles. We just need their sine and cosine values, right? I mean, because in our rotation matrices, we will take the sine and cosine of those angles. So before actually finding the actual angles, if you just find what cosine and sine of those angles are, that's sufficient. You can directly plug them into your matrices. So that's some important points. So you don't need to actually find, okay, this is 30 degrees, 40 degrees. You don't need to do that. You just need the sine and cosine of those angles. So let's call this vector U, ABC. The first step is the easiest step. translate P1 to origin, we have whatever, if the P1 has coordinates x1, y1, z1, we apply this translation. The second step is the difficult one, in which we are going to perform two rotations. As I said, it's a two-step process. Aligning u vector. If this is the u vector, there are two angles. One of them is alpha degrees around x-axis and beta degrees around y-axis. So actually, it should be the minus beta degrees, right? Because the angle that is shown here is minus beta. Because if you want to rotate around y, the positive rotation around y is counterclockwise. So here, this one just shows we need the cosine and sine sines of these angles, alpha and beta. So how do we do that? So if the u vector is this, okay, the first thing we do, what is the angle alpha? What is the sine of that angle alpha? We want to figure that out. If we call the length of this vector, the length of the vector is 1, by the way, because we made it a unit vector. In other words, a squared plus b squared plus c squared is equal to 1. All right, that's what this unit vector u is. Now, here is what we are going to do is we are going to, in order to do the rotation, we are going to think about, because we want to put it down first. So this alpha is how high this vector is above the x-axis. Okay, so in order to perform the rotation on the actual u vector, what you will be doing is, if you look at this projection of u vector, which is u prime, on the yz plane, it's nothing but the same vector in which the x coordinate is dropped. Okay, so here the u prime is the vector 0 bc. Okay, 0 bc is the u prime vector, and therefore, in order to so the length of this vector, u prime vector, is b squared c squared. Let's call it d. And the cosine of this projection of this vector u becomes, since it was bc, c divided by the hypotenuse, which is b squared plus c squared, gives me the cosine. The sine of the angle is its b coordinate was its y coordinate, z coordinate was its z coordinate. Okay, if you look at this projection, so these values give me, if I rotate around x-axis alpha degrees in this direction, in counterclockwise direction alpha degrees, I can perform this rotation by using the cosine and sine of these values. In that, I use the projection of u on the yz plane to get this angle alpha. Now, the second thing is, after you perform the rotation, u will be on the xz plane. Okay, and it's a unit vector, and I want to perform this rotation now. And this is corrected to have a plus here, as you can see, because we try to move in negative beta direction. This angle is beta. We want to rotate in negative beta direction. Now, here, what we are going to do is that, so if this is the vector u and this is its x component, the u vector is actually this vector is the summation of these two vectors. I define this vector that I try to find, this beta angle, and this its size, its sine value, and this is like the cosine value. Cosine simply is whatever its x projection is divided by the length of the u vector, which is 1, by the way. Okay, so a squared b squared plus c squared was 1 because it was a unit vector. So its sine simply becomes 1. And by the way, this formula looks complicated, but all these are 1. So this is like d, b squared plus c squared square root was d. So what I have here is d. D 0 minus a 0 1. So this becomes 0 1 0. This is 0, and this becomes a plus a, and this becomes d. Okay, a, d, and da. I have nothing more than that. Okay, so this The length of this was d. The length here is, we already called this d, and this was the a value, and a divided by d gives me the cosine and sine of these values. So the final thing, which is corrected here, we rotate minus beta degrees, as you can see, is these two steps together align my rotation axis with the z-axis. Then I rotate around z theta degrees. This is the actual rotation we want to perform, and we undo whatever we did here. We undo them in reverse order. Okay, so this is what we have in the 7-step rotation around arbitrary axis. So I actually implemented this, and it works nicely in rotation around arbitrary axis. It's not so difficult to work it around. There's also an alternative method, but we're out of time. I'm going to talk about this alternative method, which may be easier because you don't need to compute those sine and cosine of the angles. Given an arbitrary vector like this, it's possible to align this arbitrary vector with the z-axis by defining your own basis vectors which are orthogonal to each other. I'm going to talk about this. I don't want to just cram it here in this last couple of minutes. I'm going to stop here. The only thing that is remaining from these slides are this alternative method. Then we're going to finish modeling transformations and start talking about viewing transformations, the camera transformations, on Monday. All right. So that's it for this week. I'm going to stop the recording and the presentation now if you don't have any questions. Okay, I will see you all on Monday. Thank you. Have a good weekend. And as I said, we will continue with viewing transformations on Monday. Take care. Bye-bye. See you all on Monday.